Now this is the part of the lecture, the second part of the lecture on central limit theorem. Uh, and we are going to show you a couple of examples and calculation how to use the central limit theorem. So central limit theorem is the statement about the distribution or a type of a distribution of sample mean. So here is one example of usage of central limit theorem. So average math SAT in the US in 2004 was 518 with standard deviation 118. That, of course, is the for the year of 2004, which didn't really change all that much substantially up to today. But the test itself initially was curved to have the mean of 500 and standard deviation of 100. So it changes from year to year. We would have a normal distribution of the scores even for the year 2004. So that would be the X, or the single GPA of a student, would be distributed approximately normal. So that X would be approximately normal. And as stated, the mean, the expectation of this random variable is 518. That's the statement in the first sentence. And the standard deviation is 118. And we label this parameter here as variance. So we put a square here, but standard deviation is 118. That's a label for the variable. Now, the professor would advise for freshmen. So we have a question about the average of their SAT, math SAT. So this is the X bar, the sample mean, the mean of 4. Okay? According to the central limit theorem, fact A, so we said this is not really a central limit theorem, but it's a very similar statement, and we put that as a part of the central limit theorem. The fact A, this should also be distributed normally, approximately normal. It would have the same mean, which is 518. So if you take a random group of 4 students, their average math SAT would be expected to be around 518. But the variance, and we stated that as a part of the central limit theorem, the variance 180 squared for a single one becomes 4 times smaller. The sample size is 4. So the variation of the average score of 4 students, from 4 students to another 4 students to another 4 students, will not vary as much as it would vary from a student to a student. So that's the sense of the theorem. Okay, so the first question is, what is the chance that Professor Witt would have 4 students whose average SAT is better than 600? So that would be like 4 really good students on average, right? Really good students. So this is the question. You have to always be able to formulate the algebraic or probabilistic statement. So this is the statement. Probability that the average score of 4 is bigger than 600. Now once you have that, you know what you need to do. Okay, so in here I am scaling this to a z-score, right? Every time, if you want to use the tables, if you want to be able to use the tables, you need to make that kind of change. You need to z all of the numbers that are in the table, in the problem, to z values. Z values are the values for which you have tables. Without that, you would not be able to calculate, unless, of course, you use a calculator. So we know that this is done by subtracting the mean, 518, dividing with the standard deviation. The standard deviation ought to be found by making a radical of this number. But we already know this is radical on the top, which is 118, and radical on the bottom is 2. So that turns out to be, so this is the standard deviation of the x bar, not of the x, of the x bar. The standard deviation of the x is 118. The variance is square of it. Standard deviation of x bar is 59. Okay, so that ought to be used. Now, when you subtracting mean from the x bar and dividing with standard deviation, you will get a z. That's a variable, changes into z. The number 600, by the same token, 600 minus 518 divided with 59, this number here is 59, right? When you calculate that, you end up with 1.39, right? So now we have a different statement. The statement is about z, which means that we can use the tables. Now, you notice I have here approximation. That, of course, is because we're talking about approximately normal. Notice the both statement here on the top is about approximately normal. Approximately normal for the original variable and approximately normal for the sample mean variable. So now you use the tables. The tables are, before you use the table, of course, you're going to have to make sure you understand what you're doing. So the table are the tables for z. You make a little sketch. It doesn't have to be precise at all, but it'll give you an idea what you are looking for. So 1.39 is something here, somewhat like here, assuming that this would be the place when you will have an inflection driving straight. So this is 1 away from 0, and this is 1.39. So it's my depiction, of course. It's not precise, but that's good enough for you to do the calculation. So what you're looking for is above that. This is the area what you're looking for. In the table, of course, you're going to find the left tail, this area here. So below 1.39. Below 1.39, 1.39, and I'm finding the value of 91.77. 91%, 0.77%. Okay, so now I'm going to write that down. I need to make sure that I know exactly what I have. So this is 0.9177. This area. Okay, I'm not looking for that. I'm looking for the other side. So the other side is, and I have to subtract this from 100% or from 1, and I ended up with 0.0823, right? This is approximately 92%, so when you subtract 92% from 100%, you get approximately 8%, okay? I should have put also the wiggle here, because it's really an approximation. So that's the first part of the problem. The second part of the problem is looking for a chance that the Professor Witt has 4 students that are really bad in math, okay? Because the average would be less than 400 math SAT of all 4. And the average of all of the students taking SAT was 518, so this is really, really bad, okay? So again, the question had to be put in the terms of probability, that this is probability that the mean, sample mean, is below 400. Again, you have to z everything, so I'm zing this variable by subtracting 118 dividing with 59. It turns into z. I have to do the same thing with the number 400. 400 minus 518 divided with 59 turns out to be a very nice number, -2. So As a matter of fact, I don't need an approximation here, actually. This is exactly equal. Check it out. Negative 118 divided by 59, that's 2. Negative 2, of course. So I'm going to change this. I'm just going to change, I forgot to change it into the lecture. I have to actually use equals here because I didn't approximate. Now I'm going to approximate. So this is going to be the approximation. All right. So how do you find that? Again, the story goes into tables, but again, you need to know what you're looking for. So standard normal tables, nothing special. Just make sure you got something that looks like it. And the number negative 2, this would be 1 away from the mean, so this is negative 1. Negative 2 would be like maybe here. Okay? And you're looking below that, so you're looking for something really small, this sliver of area. So that's easy to find in the table, and the table you're going to be looking for negative critical values. Negative critical values is the second page of the table, so you get negative 2 to look at. And negative 2 is right here, and the second decimal is also 0. So we are dealing with the approximately 2.28% according to the tables. All right, looks good. All right, the third question is that what's the chance that this average of those 4 students is above 500 and below 600? It's kind of like what you would expect to happen. So something, you know, around 518, but this is on a better side, right? A little more than 518 on the one end, but a little less on the just a little less on the other end. So. Okay, so again, you have to change the question into the probability business. I mean, you have the word, you have the sentence with words. Now you have to write that in terms of a probability, in terms of algebra. So this is probability that the sample mean of 4 students SAT is above 500, see, bigger, right? And less than 600. And again, the same goes on like in the previous questions. I want to use a table. I'm gonna do that by z-ing everything. So z this guy, you got the z. 500 minus 518 divided by 59, you get negative 0.31. And 600 on the other side, 600 minus 518 divided by 59 is 1.39. This time you have to be a little more careful because you're looking for a strip, area of a strip. So again, you make sure you make a sketch to make sure you know what you're looking for, and that way will help you to find it. Negative positive 1.39 would be something like here. Okay, so this is at 1 approximately, so 1.39 is a little bit further, and negative 0.31, that's closer to 0, right? So maybe like here, right? So that's what you're looking for. All right. Oh boy, I have to remove the piece by piece. Okay, so this is it. So you're looking for the area of this strip. Okay, 1.39 is one end, and the other end is negative 0.31. Right. Right. So again, the plan here is to find the bigger area and then the smaller area, and the bigger area is up to here, the smaller area is up to here, and then to subtract them. Okay, that would be the idea. We're gonna make it a little lower. Okay, so this bigger left tail is up to 1.39. 1.39. Oh, okay. I already have that for somehow. I just had that before. 0.9177. Okay. The area, not the length of a. Don't think I'm doing the length of the arrow. I'm talking about the area of the tail, but I'm not going to write inside. I'm going to write outside. All right. Squeeze that a little bit. And now up to negative 0.31, up to negative 0.39. Negative 0.39. Right? Oh, excuse me, negative 0.31. That will be here. Sorry. Negative 0.31. Okay. Looks like 38%. 37.83%. 0.3783. 0.3783. So this piece here. Right? 0.3783. Looks good. Now, if you subtract these two numbers, you end up with 54%, approximately, right? So that's, you can check that out. It's not really that difficult to subtract these two. You end up with 0.5394, which is approximately 54%. So chance of that happening is approximately 54%. Okay. Another example. In here, we are talking about a shipping company that charges an extra amount of money if the shipping load during 1 week period exceeds some kind of contractual limits that they have, 20 tons per container. So which means that they're shipping, they expect to ship 20 tons per container. So they don't want that to be above that. So if it happens that, you know, the average over 1 week, it could happen occasionally. You have something a little bit above, something a bit below, and so on. But they expect the meat packing company to follow the container capacity, which is 20 tons or less, right? So they have a contract in which they will charge this meat packing company more if they go during 1 week on average above 20 tons, right? So that's what we're told. So which means we are dealing with a shipping load. The X is a shipping load. And that is a variable. We don't know what kind of variable that could be. Nobody says it's a normal random variable. But now we know that the meat packing company ships on average 18.5 tons. So we know that this random variable, the shipping load, from a container to a container, right? I'm not going to write that. Random container shipping load has a mean, and mean is the expectation of random variable, right? It's 18.5 tons. So kind of close to 20 tons. Because of course they want to use the capacity, right? They don't want to ship half-empty containers. And it also has a standard deviation. The standard deviation turns out to be 7.4 tons. So this is the standard deviation of a single shipping load, a single container. So there is a variation. It's a pretty big variation, actually. And so it's basically, you know, what you could expect. Sometimes you have a lot, sometimes you have a little less, depends whether you're shipping and so on. Okay. Now, let's say they are shipping 69 containers this week. That's a lot of containers, but, you know, like a 10 a day. So they're shipping approximately 68 this week. What's the chance they're going to have to pay this extra fee? Which means, what is the chance that the average shipping load of 68 containers will be above 20 tons? Okay, now we have to ask question here. How do we know that? How are we going to find it out? We don't know nothing about the X distribution of the X. And here we are asked for a distribution of X bar. Well, we have a central limit theorem. So central limit theorem says that X bar is approximately. So this is now, we are using the fact B of central limit theorem. The X bar is approximately, by the central limit theorem, normal. Okay? And it has the mean, the same as mean of X, which is 18.5. And it has the variance 68 times smaller than 7.4. 7.4 is standard deviation, actually. I should say the variance would be a square of that, which would be something like 50 something, a little more than 50. Okay, but we're gonna have to divide that with a 68 because that's the size of the sample, and we know that the variance of this guy is 60 times smaller than the variance of single container shipping load, random container shipping load. Okay, so now we know that this random variable is normal, approximately normal. In other words, we can now use the calculation by using the what we know about the normal random variable. So this is the question. What is the chance that the shipping load average of 68 containers is going to go, the average shipping load is going to go about 20 tons? You have to z this number, you z this number, you get z. You z 20, you have 20 minus 18.5 divided with the standard deviation. Standard deviation is radical of this. Radical of the top is 7.4, radical on the bottom. Well, you're going to have to find the radical of 68. But when you do this calculation, so this is your calculator business, 20 minus 18.5 divided with this, whatever this number is, ends up with approximately 1.67. Approximately 1.67. Then one more time, you're back in the business of trying to use the z tables. So again, you need to know what are you looking for. Above 1.67, so this is approximately 0. This will be approximately 1 away from 0, so you're coming somewhere here, 1.67. And you're looking for this area, above 1.67. Why did I write 9? I don't know. 67, right? Let me make it into a 7. Right, a lousy looking 7, all right. But anyway, I know what I'm looking for. So I am going to look at the tables again, up to 1.67, up to 1.67 positive, 1.67 is this number, 0.9525, 0.9525. But I'm looking for this end, this other side. Right tail, left tail is 9525. That's everything in the tables are left tail. So this piece here is the what is the difference between the 100 and 95.25? And that is 4.75%. We're talking about percent, but you always do the calculation just with decimal numbers because that's easier to work with. So 1 minus 0.9525 is 0.0475. Okay, we use the power of central limit theorem, the fact B, to get this approximate calculation. This would also be approximate, of course. Even with the table, I get approximation, approximately 5%, right? 5% chance. So there is a 5% chance that this load would exceed, on average, 20 tons. 68 containers could exceed 20 tons on average. That would be, once out of 20 times. So this 5% is one out of 20, which means that in the course of 1 year, that would happen at least twice, maybe more. Okay, so they have to put it on their bottom line that they will, if they keep on shipping like that, they will twice a year they will have to pay an extra fee for that kind of shipping. So whatever works for them. If this is not good enough, then they have to be loading less their containers to pay attention to that kind of stuff. Okay. I could have calculated this by using the calculator, so I'm going to do that just to give you an idea how to do that. So using calculator without using the tables, I would need to use a distribution here, normal CDF, and the distribution is asking me, so I'm going to clear it up. Distribution is asking me for a lower end. Now this 20 here is a lower end, right? It's above, it says above 20. The upper end or the upper side would be anything really big. You can put anything. You should actually put plus infinity because you don't have the upper end here. In this inequality here, it says the x bar is bigger than 20, but doesn't say what is less than. So you should put them like infinity, but you can put it in a calculator. So you put something really, really big. So I put here 1 million, that's gonna 10 million, so that's gonna stay. And so I got that, and I'll keep it. And I have the mean 518, that's from the SAT, but this time I have the story here 18.5. And the standard deviation is, well, it's, I know, 7.4 divided with radical of 68. And even if I don't know what that is, I can put it in the calculator. The calculator will do the calculation. So it's right here. I was already doing that here. And finally, I need to do the call for the instruction in the calculator. And the calculator says 4.7%. Slightly different than what I got. I got 4.5%, right? Not a big deal. This is a... actually I got 0.475. Oh, okay. So this is really, really minor difference. I mean, I'm getting here 4.7%. I'm getting here 4.7%. And if I go, to 100%, then I get a difference of 5 in the table calculation and in calculator 3. So that's not much of a difference at all. So this is a 2% over 1%, not big deal. Again, the calculator is more precise because the calculator uses calculus calculation, while the tables are using 4 decimals, which of course is going to be some error on the way when you calculate that. Okay, I want to show you another thing about the central limit theorem. How powerful central limit theorem is. So we said you use the central limit theorem fact B if you have the sample size 30 or more. So this is the sample size that we consider to be big. And generally you would like that to be as big as possible. Okay, but I'm going to show you that this actually works even for a much smaller sample size. At least you can see how central limit theorem assembles even on the smaller sample size, that the fact start to have some power. So let's say that I have a five-sided die, not a six-sided, but five-sided die, whose sides are 1, 2, 3, 4, and 5. I'm using a five-sided die because it's easier to calculate with 5 than with 6. Okay, so let's say I have something like that. Now, if you roll that die, it's equally likely to be on either of the 5 sides, right? So it has 5 faces. One face is another one, 2, 3, 4, and 5. Okay, they're all equally likely. So 20% that you're going to get 1, 20% you're going to get 2, 20% you're going to get 1 out of 5. that you're going to get 3, 1 out of 5 you're going to get 4, 1 out of 5 you're going to get 5. So this is the, the probability histogram of the distribution. You have 1 with a chance of 20%, 2 with a chance of 20%, 3 with a chance of 20%, 4 with a chance of 20%, 5 with a chance of 20%. This is nothing like normal. This distribution here is what we call uniform distribution. Everything is equally likely. Okay? Now, I calculated, of course, the mean. What's the mean? 3, of course, on average. 3, right? That makes perfect sense. And the standard deviation I calculate also is radical 2. Okay, you can do it yourself. You just write the random variable. The values of the random variable are 1, 2, 3, 4, and 5. And the probabilities, so each one of them is 0.2. So 0.2 for 1. So this is the probabilities. That's a distribution for this random variable. 0.2 for 2, 0.2 for 3, 0.2 for 4, and 0.2 for 5. Okay? Now, you remember you were doing this calculation for any kind of random variable, you can do it here too. So on average, it's going to be 3. That makes perfect sense, because it's equally likely to be 1 or 5, 2 or 4 or 3. So on average, it's 3. But the standard deviation, it's a little bit harder to understand why it would be radical 2, but you can do the calculation, and you can find that out that is indeed a radical 2 standard deviation. Now, here is the table in which I'm taking a, triple roll of this kind of die. What can I possibly get? It's all equally likely. I could equally likely get 1, 1, 1 or 1, 1, 2. So that's a sample. Or 1, 1, 3 or 1, 1, 4, 1, 1, 5. And on you go. So I can get equally likely any one of those guys here and everything else. I listed everything possible you can get. You can get like 4 on the first roll, 1 on the second roll, 1 on the third roll. Okay? So that's a triple roll. So it's only 3 things. All right? Now if you calculate the average of 1, 1, 1 is 1. The average of 1, 1, 2 is 1 and a third. The average of 1, 1, 3 is 1 and 2/3. The average of 1, 1, 4 is 2, right? 1 plus 1 plus 4 divided with 3, that's 2. And so on. Every one of these guys, every one of these triple rolls, like triple roll here, I have a triple roll, 3 on the first roll, 1 on the second roll, 4 on the third roll. An average of these 3 is 2 and 2/3. Okay, I wrote that as an improper fraction here, but excuse me, as a mixed number, but you would understand, how to get that if you really want to get decimal number. I just wanted to keep the fractions. I want to make sure that I have this done properly. All right, so those are all the averages. Everything that could possibly happen is here. That's the whole population, and all are equally likely. Right? Now try to make a histogram of this thing. The X bar. I'm trying to make a histogram of the X bar. Right? You can see that you're going to get 1 only once. There is no any other way to get 1 than by 1, 1, 1. The only way you can get an average 1 if you have 1, 1, 1. If you have anything bigger than 1 on any roll, it's going to be bigger than 1. Right? But you can get 1 and 1/3 in a couple of different ways. You can get 1, 1, 2. You can also get 2, 1, 1. And you can get 1, 2, 1. Right? In all 3 cases, this is the average is going to be 1 1/3. And so on. There's lots of different things you can get, but you can get anything on average, anything between 1 and 5. And 5 you can get, of course, as 5, 5, 5. That's it. Okay? So I counted all of this stuff. And this is what I got. I got 1 once only. Again, all of those rolls I can get 1 once. I can get 1 1/3. 3 ways. I already told you there were 3 ways. I can get 1 2/3 in 6 different ways. I can get 2 in 10 different ways. I can get 2 1/3 in 15 different ways. You just go and count 2 1/3. How many times 2 1/3 is in this table? And I'm telling you, if you do proper count, it's going to be 15 times. 2 2/3 is 18 times in the table. 3 is 19 times. 3 1/3 is 18 times. 3 2/3 is 15 times in the table. 4 is 10 times in the table. And we can even calculate it. I will just convince you. 4 is exactly 10 times. All right, you don't have any 4 here in the first column. You have 1 here. 1. That's it. In the second column, in the third column, you have it. 2, 3, 4. Oh, 2 times. That's just 4 and 1/3. So I have total now so far 1, 2, 3. I shouldn't lose that count. 3 so far. 3, 4, 5, 6, 7, 8, 9, 10. Exactly. Okay? So again, you convince yourself that this is properly done. I get 4 1/3, 6. Again, there's 6 times in the table. 4 2/3 is 3 times in the table, and 5 is 1. Okay? What's this histogram looking to you? I guess it looks like a normal distribution. Now, of course, it's not normal distribution because it's a vertical bar graph rather than a curve. When everything is smooth, you have a jagged, sort of jagged curve. But if you do make an overlay, and I'm making an overlay, and guess what overlay I'm going to use? I'm going to use an overlay that is a normal distribution with the mean 3 and with the variance 2. Okay, I should write that. Mean 3 and the variance, standard deviation is radical 2, but the variance of course is a square of standard deviation, so that would really be 2 for a variance. Okay, so this is one of the 2 ways to write this. So we write here the mean, and here we write the variance. All right, but you might think about it when I write like that, and I always write it with a square. You think, oh, maybe you forgot the square here, maybe the variance is 4 and the standard deviation is 2. No, I didn't forget the square. This is really the variance, so maybe this is better to write this way, in old fashion. So we have mean, we have standard deviation with the square. Okay, that's this red curve. So the mean of 3 rows is distributed close to normal, which is a surprise. Oh, okay, excuse me. I need to divide this by 3. Yeah, I forgot to do that. Yeah, I'm saying that the red one has the variance that is 3 times smaller than the original one. Yeah, that's what the central limit theorem says. So central limit theorem says, you know what? You are going to have, if you make an average of 30 rolls or more, you're going to have a normal. You're going to have a normal distribution. But I'm saying, even if you only take 3 rolls, you already see that this average of 3 rolls assembles into distribution that looks very much like normal. And if you put the central limit theorem conclusion, what it should be as a normal distribution, which is an average of 3 and a variance of 1/3 of 2, as an overlay, it really perfectly fits this as an overlay. Beautifully. Okay, you can say, well, it's a little bit too high here, it should be a little bit lower. But yes, you're right, this is not a normal distribution because the sample size is too small. But if I make it this lower, of course, I'm going to have to expand these sides, and then I'm going to be moving away from the bars, so I can't really do that. So it's not a perfect normal distribution, of course, but it does come close to it, which is amazing. So for the sample size 3, now for my own entertainment, I made a sample size 5. That's even closer to it. I'm not going to bother you with that, but that's, if you keep on increasing the sample size, it gets closer and closer to the normal distribution. So you can see that nature does like normal distribution. It forces when you keep on increasing the sample size, it forces distribution of the mean of that kind of sample to be closer and closer and closer to normal. And that's why we call normal distribution, because it seems to be, maybe you should call it natural. It seems to be a natural distribution. Okay? So again, my initial distribution of a single roll was uniform. Everything was equally likely. It was a flat top. But when you look at the average of 3 rolls, it becomes really close to normal. That should give you an idea of the power of the central limit theorem. Again, everything we do in the sequel of this course, and in the statistics too, if you ever take statistics too, most of the stuff, and I shouldn't say everything, but most of the stuff will be related or a consequence of a central limit theorem, which makes the central limit theorem for us the single most important theorem in the whole course that we have, the single most important fact in the whole course, which also puts a pressure on you because you have to learn it. Okay? Because if you don't learn the central limit theorem, if you don't do the homework, you don't understand what it's about, you will not be able to follow a good chunk of the stuff we're going to be doing in the sequel. So I strongly suggest you to do the homework on the central limit theorem, which is the C part of the homeworks on the normal under variable. So it's A, B, and C part. C part is about central limit theorem, and you will be practicing this a little bit. You can use a calculator, you can use tables. You should be able to use both. Okay? That's my story for the lecture on the normal under variable. So central part 2, the central limit theorem part. I should say lecture central limit theorem. Okay? Next time we meet, we're going to move on, and we're going to be studying the estimation, what we call it, estimation theory, for which normal distribution and central limit theorem will be very important to know about, because you're not going to be able to study, which is the same old stuff every time you have mathematics. Everything is connected, right? So I'm going to stop the stream, and we are done for this lecture.